Welcome back. I got a few questions on the homework that I said I would start out with. Actually, I only got one, and then I'll ask you if you have any more. But so the question I was asked was question one. But I just want to tell you a few things about question three. I did just post Friday's video and module and notes, although I posted Wednesday's module with notes that extended to Friday. So I think if you go into Friday's module, it'll say under notes, see Wednesday's module. So you do have everything you need for this, but in case you don't want to go through the notes or the videos to look for them, just remember the formula we computed last time for the mean Q length and equilibrium for the MG1. So this is the mean Q length, which is actually all people in the system, which is what's being asked here. And equilibrium for this Q. And we derived this last time. We got L is 2 lambda over mu, and I'll go back and define these parameters, plus lambda squared sigma squared minus lambda over mu squared over 2, 1 minus lambda over mu. And the M in MG1, so this is what you would need for part B. The M in MG1 stands for memoryless, and that means the inter-arrival times are still exponential, and so Poisson again. And so the lambda is the arrival rate. And the mu, just like before, is the service rate. And this is 1 over the mean time for service, 1 over the expected service time. And so you'll just have to look that up for the gamma distribution, although I wouldn't go looking on the internet because it's going to be like 60-40. Someone's going to parameterize it one way versus another. So in this class, if X is gamma alpha beta, then the expected value of X is alpha over beta, where in other places you might see alpha times beta. Okay, and part A says, what is the probability that an incoming customer has to wait for service? This is just the probability that there's someone in the system when they arrive. And we've only computed 2 quantities for the MG1Q, the expected Q length and pi 0. So I think you can get A from pi 0. Okay. So I specifically got a question to go over one. In problem 1, there's not much new stuff on this homework. This could have been on the last assignment. It is a birth and death process. No, it's not. I'm sorry, it's not. It's a discrete time. Well, let's see. Let me try to find the generator here. So I'm going to let 0 be the machine is in repair, and then we have all the other natural, like 1, 2, 3 up to K, being the different states of repair. And then state I is in repair state I. Yeah, we can treat this as a birth and death process. For a minute, I thought we had to do it as a more generic continuous time Markov chain where we had to solve pi times Q equals 0. But let's see, we're in repair for an exponential amount of time. No, sorry. It's functions for an exponential amount of time with rate lambda and then fails. So the rate of increase, because it fails when it goes to repair state 1, and then it goes to 2, and finally it goes to K, and then it comes back around. So the birth rate, the rate of going from 0 to 1 is just the rate of the repair time. And oh, working, yes, that should be working. 0, machine is working. Thank you. So if we could jump like by more than, well, I guess it's not though. We go all the way down from K to 0. Ooh. I guess I can't treat this as a birth and death process. For the birth and death process, I need the rates of increasing or decreasing by 1. And I thought I was okay because I only increased by 1 at a time, but I decreased all the way down to from K to 0. Yeah, it's kind of birth and extinction. So I guess I'm going to have to go for it with a Q matrix. So we've got 0, 1, 2, k minus 1 up to k, 0, 1, 2, k minus 1 up to k. And so we go from 0 to 0 with rate lambda, and we do not jump from 0 to any other state. And because these need to add up to 0 in the rows, I get negative lambda here. We go from phase 1 repair to phase 2 repair with rate mu1. That's the exponential amount of time that you're in phase 1 repair, and then you jump to phase 2. And that's the only place you can go. So mostly we have zeros, except on the diagonal, we're going to get negative mu1. And I'll just say a couple more rows here. From row 2, you can only go to state 3 with rate mu2, or you can stay where you are with rate negative mu2. And so that's going to continue. Let me try to make some rows here so you can see where things are in this line. If we're in state k minus 1, we will move up to state k with rate mu sub k minus 1, or we will stay where we are with the negative of that. And finally, if we're at rate k, we're going to drop back to rate 0 with rate mu sub k, or we'll stay where we are with rate negative mu k. So unfortunately, that last drop, which is more than like 1, we're going to have to treat this as we're not going to be able to treat this as a birth and death process. So I would look into solving, I would just solve pi times q equals 0. And then, the answer to part A is the proportion of time the machine is undergoing a phase I repair is pi sub I. And the answer to part B, the proportion of time the machine is working means we're in state 0, so pi sub 0. Okay, so problem 2 is this one, in fact, is a birth and death process. So we can use the old pi n is lambda 0 times up through lambda n minus 1 over mu 1 up through mu n times pi 0. Each individual is assumed to give birth at an exponential rate lambda and to die at an exponential rate mu. So if there's 0 people in the population, then the only increase is immigration, and that is rate theta, because there's no one there to give birth. And if there's one there, then so this means there's one individual, and the rate until birth is lambda, but this event that cell or person gives birth is racing the immigration clock. So this is racing with immigration. So what happens next is the minimum of 2 exponentials. And so we're taking the minimum of like an x and a y, where x is exponential with rate lambda and y is exponential with rate theta. And that's going to be the sum of those rates. Okay, I think this would be really hard to get a closed form expression for, but fortunately I gave you some numbers. And well, immigration. So there's no upper bound here. The n equals 3 does not mean that that's the max population size. That's just the max. Above that size, we don't have immigration. Okay, so lambda 2, there's 2 people racing to give birth. They each give birth after an exponential amount of time with rate lambda. So they're racing, so that's 2 lambda, and then immigration. Immigration is not allowed when the population size is n or larger. So I am going to write this out for n equals 3. So lambda 3 is just 3 lambda, and there's no immigration because we've hit that place where there's no immigration. Lambda 4 is 4 lambda. But they always die with an exponential rate mu. So mu 0 is always 0, and mu I is mu for I greater than or equal to 1. So I was hoping that just the first few terms were going to be messy and that you could get a nice expression for the tail of the series, but those things always appear. You always have lambda 0, lambda 1, and lambda 2 in your pi 3, pi 4. So now I don't know if this is going to come out nicely. So you might have to do it numerically. But you would just use this pi, and the answer, the proportion of time that immigration is restricted, is it's restricted when there's n or greater. So you really want to add up all these guys, or 1 minus adding up the rest of them, which is not going to be bad when n is 3, because you'll only have to add up pi 0, pi 1, and pi 2 and subtract it from 1. Does that make sense? I did get a question on 5, so that's where I'm going next. I gotta mute and talk. Okay, 5. So we've got an MM1 queue. So we've got a single server. So it's like empty, and then someone comes in, and then someone comes in, and then someone leaves, comes in, leaves. And we talked about three things. One was pasta. If you grab values just before a jump, and if you can compute the transition probabilities between those yellow dots and compute the stationary distribution for that discrete time process, you will in fact have the same stationary distribution as the continuous time process, which, by the way, we know for this is 1 minus lambda over mu, lambda minus mu to the n, assuming lambda is less than mu. We also talked about the post-departure process. So if you grab points just after a departure, it would be here and then here. Well, only departures, huh? No, yes, okay. Then it would have the same stationary distribution. But in this problem, you're being asked to grab every point when there's a change. So you could start here, grab this, and then this, and then this, and then you go along, and the next transition is up here, and the next transition is up here, and the next transition is down here. And so that's what we're looking at in this problem. And we showed in class that the stationary distribution, I might have this backwards. I think we showed that the stationary distribution for the original chain is proportional to the stationary distribution for the new chain over Qi. You know what? You don't need this at all. You don't need this. So in part A, you want to write down the transition probabilities for this discrete time chain. And so from state 0, you always move to 1 at your time of your next transition. So this is going to be probability 1. So Pi plus 1, and this is for I greater than or equal to 1. This is equal to the lambda over lambda plus mu, the birth rate over the rate to the next transition. And Pi minus 1 is going to be the death rate over the total rate to the next transition. I might make my life a little simpler and call this like P, or P might be confused with the subscripts, like call this Q and 1 minus Q or something like that. But in part B, you want the stationary distribution for, so what I meant by part B was not to use that proportional formula with the pi hat, but to actually find the stationary distribution for a chain running like this for this particular kind of poor embedding, because it won't have the same stationary distribution as the continuous time process, because we didn't do pasta or reverse pasta, and we didn't adjust by dividing out the rates, that formula I just showed and erased. So this is just, you have P01 equals 1, Pi plus 1 is this Q, Pi minus 1 is 1 minus Q, and your state space is 0, 1, 2 on up. And this is just a find a pi problem. So this takes us back to the beginning of class. This is just solve for pi for this system. It won't be that you get the MG1. So you're not going to get 1 minus lambda over mu to the n, because it wasn't embedded properly. So it turns out that if you adjust this one and allow yourself to go from 0 to 0, like a death, like a reflecting, like an absorbing, not absorbing. What do you call that kind of boundary? So you're trying to go down when you're at 0, and you obviously can't because that's not part of the state space, but you can stay flat. So in part C, you can go from 0 to 0. And so in one time step, I know this doesn't look like our normal step function, but you have an option of going up to going up by one state, given the birth rate and over the total rate. And you have the option of going down or staying flat. That's what I was trying to convey when I wrote that. You can move from 0 to 0 with probability mu over lambda plus mu. And so you just want to show, so you've got I plus 1 is always lambda over lambda plus mu. I minus 1 is always mu over lambda plus mu. That's kind of what it was before, but it didn't hold when I was 0. So you just want to show that the stationary, you have a couple options. You could look at the stationary distribution. I would look at the stationary equation. I would plug these guys in. And I want to make sure that this holds when you use, like, pi I is 1 minus lambda over mu to the I. That's lambda over mu to the I. So it's just a matter of verifying this when you're using this for the pi's and these for the p's. So we didn't do pasta or reverse pasta or really the other thing where we renormalize things. We just changed up one probability, one transition from 0 to 1. And we get something for which the continuous time stationary distribution listed down here will hold. All right, we should probably do something new today. We are on a simulation break. Oh, wow. See, I just pepped up thinking about the Metropolis Hastings algorithm. It cured me of my illness. We were about to do our first Markov chain Monte Carlo algorithm, and I'll write those words down and tell you what that means. But I wanted to recap again our notation because we are moving for the first time into continuous state space, but with discrete time. So thought break, this is something completely new. Discrete time, continuous state space, Markov chain notation. So before meaning discrete time, discrete state space. I never used that abbreviation before and will never use it again. We had transition probabilities. You can move from some state I to some state J in 1 unit of time. And now I'm going to call it P of X comma Y. And you can even use I and J, but usually I and J look like discrete things to me, but you could use it. And before we had a pi I, and now we have a pi of X, which is actually a continuous probability density function. Okay, and before we had our stationary equation said that pi j is the sum over pi j, where you sum over all I in the state space. And now it's pi y is the integral of pi x p xy dx, just the analog of that. And by the way, the analog of summing the pij over all j being 1 is now integrating over all y. We're going to get 1. And an example of a kind of continuous transition density, so that's what I would call this, a transition density, might be that, as an example, so here's a pxy, it might be when you're at x, you want to draw the next value from, say, for example, an exponential distribution with rate x. This assumes that the state space is all, everything is greater than 0 here. We can't have a negative rate or even a 0 rate. So to envision this, if you're currently at some point X, at the next discrete point in time, you would have a kind of exponential distribution, which has most of its area piled up down by 0. The picture looks like this. And so you're more likely to end up here than you are over here. And the actual transition density would look like x e to the minus xy. And you know how to draw exponentials. But if it wasn't an exponential, then you probably want to use built-in functions from this point forward, not only in the rest of the class, but in the rest of your life. I keep making you like generate random variables from scratch. But a really common transition density here is to draw the next value from a normal distribution centered at x. So that is all the notation. And we are ready for our first Markov chain Monte Carlo algorithm, or MCMC algorithm. Monte Carlo algorithms are anything that have to do with some randomness and probability. And Markov chain Monte Carlo algorithms also have to do with Markov chains. So here's the setup. There is no Markov chain in sight. There's no Markov chains. We're going to create one. And then we want to draw or sample values or simulate from a distribution with PDF f of x, which I'm about to change. But this is presumably a continuous PDF or probability density function. The algorithm we're about to talk about is would actually work in a discrete case, but I'm really not sure why you would do that. You would have better options in the discrete case. And so the idea is that we're going to create, and there's several algorithms that will do this. We're going to create a Markov chain with stationary distribution f of x. So you would simulate it for a long time and grab output as approximate draws from f of x. Or perfect draws. By Friday, we should get to perfect simulation. And that's really the end of the course, because Monday is going to be a review. Oh, wait, Wednesday is the last day. So, sorry, next Wednesday is going to be a review for the final though. Okay, and grab output. So this is maybe not the setup. I thought I was starting the algorithm, but the scenario for a Markov chain Monte Carlo algorithm. And the particular algorithm we're going to talk about today is the Metropolis Hastings algorithm. I feel like I did this last time. Maybe I gave the spoilers in my last 5 minutes talking fast. Did I write out this algorithm? I'm just going to keep going, but someone tell me if I already did this. Okay, I did tell you, I remember this, that Metropolis first developed this algorithm in the 50s for the Ising model of a very simple model of magnetism in physics. You've got a square lattice grid and it's really large, not like what I'm drawing. And it's got on each side little pluses or minuses, and they represent little magnet vectors that it's kind of overly simplified, but they can only point in 2 directions, up or down. And another way this is drawn is a lattice like this, and like an up here and a down here. And so you've got these ups and downs, blah, blah, blah. And there's a particular model for this that I'm going to show you next time, but basically, given certain parameters, these magnets want to be aligned. So I'm not on camera, but imagine, all right, hold your left index finger up and your right index finger down next to it, pointing down, and then shake your hands a little bit. Now that's 2 magnets pointing in a different direction, and they're kind of like confused, and then one flips to match the other. That's what's going on here. And over time, it'll eventually reach an equilibrium. And there's actually external temperature parameters as well. But in the 50s, Metropolis came up with an algorithm for this specific problem. In the 70s, Hastings generalized it. So now it's used for a whole lot of problems. And for the longest time, it was called Hastings Metropolis. But in the very late 90s, around 98, there was this campaign to put Metropolis first. So, okay, so the target here is, and this is the one I'm going to cross out. So some probability density function f of x. But because we're doing a Markov chain Monte Carlo algorithm, we're going to run something for a long time until it converges to this. I'm going to go ahead and call it pi of x because it's really going to take the place of the stationary distribution for this chain we're going to simulate from. And x can be very high dimensional here. It often is. I've done the Metropolis Hastings algorithm where this x was 2 to the 500 by 500 dimensional. It can be quite large. Doesn't have to be. Okay, and the idea behind any Monte Carlo algorithm, Markov chain Monte Carlo algorithm is to create a Markov chain that converges to it. So you're gonna have to choose a so-called candidate transition density or PDF. And I'm not gonna call it PXY because it's not gonna be ultimately what we're using. I'm gonna call it Q of X and Y. So this will probably have some X's in it, although sometimes the next value drawn is independent of where you are, but you do need it to be a PDF in Y. Okay, and you start at an arbitrary value. What do I mean by start? We're starting a Markov chain. You just pick some place to start. I don't know. X0 is some X0. And we have everything we need to now describe the algorithm. So this is kind of like pre-algorithm steps. You need to find a candidate transition density and pick a starting point. And other than that, we're ready to go. So here it is, the algorithm. So before I start my little loop here, I'm going to say we're currently at X. So I had a discussion with myself in my fevered madness this morning, whether or not I was going to write this. And then at the end, I was going to assign this and then say, let n equals n plus 1. But I think I'm just going to say you're at X, and here's how you move to the next point. So presumably at some time, you're at X. So maybe X0 if you're starting. Okay, so step 1 is to draw or simulate a value Y from the probability density function that depends on your current value and is a function of Y. It's a PDF in Y. Like we had this exponential example today. And the second is to draw or simulate a uniform 0, 1. And the third is if the uniform 0, 1 is less than or equal to something that's always called alpha xy. I know that looks like proportional to, but that's an alpha. And I think it's an alpha because that's a Greek A and it stands for except. And this is defined. I don't know if everyone knows that notation. So this is defined to be the minimum of 1 pi y q yx over pi x q xy. Weird, right? Why would you do that? Because detailed balance stuff is coming up. Okay, so if that's true, then you kind of accept this, but you always move. You don't have a rejection where you don't move. So your Markov chain will move to this new value, or it will move forward in time and stay flat. So yeah, now I regret this, the notation. I'm so sorry. I'm gonna go back up here. And I'm going to say the current time is n, and then x at time n is some x. So if the u is less than or equal to the alpha, and you might want to put n subscripts on these guys, but it's just an algorithm. You go through this each time with new u's and y's. Anyway, if you accept, then xn plus 1 is the y value, the value that you drew from this. Otherwise, you stay flat, but you do move forward in time. So you stay right where you are, and then, I don't know, set n equals n plus 1 and return to step 1. Okay, let me convince you that this is converging to the right stationary distribution. One of the things I forgot to recap at the beginning when I had the list like Pij is now P of xy was detailed balance or reversibility. So maybe I should say before proving that, detailed balance is now, in this case of a continuous state space, it's now pi of x, pxy equals pi of y, pyx. And I'm claiming this two-step procedure of drawing something from Q and accepting it or not accepting it. That's defining a pxy for us that I'm about to write down. And it's going to be reversible with respect to the target distribution. And if you have that detailed balance, then if I integrate both sides with respect to, say, x, then I get the other side with respect to x. And in that case, I get to pull out the pi y. And pyx integrated over x, that integrates to 1. That's like the analog of saying the y row of a matrix sums to 1. But we get the stationary equation. So as usual, if you have a stationary distribution, you don't need to have detailed balance or reversibility. But if you have it, then you have a stationary distribution. And so I claim that we have, or Metropolis, actually Hastings claimed that this recipe gives us detailed balance. And it's pretty easy to show. I once proved this the long way by trying to show that this stationary equation holds without using detailed balance. And it took 3 pages and it was really ugly. Detailed balance is great when you can use it. Okay, so in the Metropolis Hastings algorithm, the probability density function starting at x, the PDF in y. I'm going to say probability. This is not a probability. These are continuous, but starting at x, now I'm doing air quotes that you can't see, the probability that we go to y is just the probability that we draw the y from this candidate density times the probability that we accept the move. This is at least for y not equal to x. If y is x, you would say I drew that with 0 probability because I'm drawing from a continuous candidate qxy. But we can also say the probability you go from x. So sometimes you'll see this in brackets in Markov chain stuff. And that is emphasizing that that is something you can actually reach with positive probability. So this pxy is a PDF in y, but it's kind of a mixed PDF. You can, starting at x, you can choose x again. But if you don't, then you choose according to this PDF. So if you wanted to write down the second one, you would have to say, oh, I'm leaving room for an integral. I'm going to choose a y, and then I'm going to fail to accept it. And I'm going to run that over all y's that I could have chosen and failed to accept. But this is really the interesting one. So check this out. The pi of x, pxy, is equal to pi of x times q of xy times alpha of xy. okay? And the alpha was defined as this big min thing. So I've got pi of x, qxy, and then the min of 1, pi of y, qyx, over pi of x, qxy. So I'm going to multiply this through, and this is just sort of like, if you have 2 times the minimum of 1 and 3, the answer here, because everything is non-negative, is the same thing as the minimum of 2 and 6. Like you can bring that inside and multiply. So I get the minimum of pi of x, qxy, and then when I multiply by the second one, the denominator cancels, so I get pi of y, qyx. And now I'm going to use the same sort of trick, but I'm going to pull this one out front. I'm going to pull that out, and I get pi of y, q, yx times the minimum. So in order to multiply that out and have that make sense, I'm going to have the first thing here be the, I don't know why I started using brackets. It's not wrong, but before I used, I guess I did, whatever. Okay, so this is going to be pi of x, q, x, and qx and y, sorry, over pi of y, q, yx, and then 1. Because if you multiply that in, you'll get this back. And so this is just alpha yx. Sure, the minimum was written in a different order, but it's like saying the minimum of 1 and 3 is the minimum of 3 and 1. Doesn't matter. So we've got pi of y, q, yx, alpha yx, and this was our pyx. So we've got pi of y, pyx, and we started with pi of x, pxy. And so we have shown in the case where y is not x, we've got reversibility or detailed balance. And we just showed up above that that's enough to give you that pi is stationary for the chain running according to the transition density P. So this implies pi is stationary for the chain running according to P. I mean, the other point where y is x is just kind of you saying pi of x, but notationally, I would have to say a little more here about that positive probability point, but it's essentially you saying, yes, pi of x pxx is pi of x pxx. So reversibility holds there too. But I didn't want to get into the discussion about the brackets, and so I'm just going to pretend I didn't say that. So that's why this algorithm, that's why they came up with this, formula, this acceptance rule. And a lot of algorithms are constructed based on reversibility. Just imagine that you have a distribution you want to draw from, and you want to create a Markov chain that converges to it, and maybe Metropolis Hastings isn't working so well. What do I mean by that? If you choose your candidate density poorly, you may have very few acceptances, and you'll just have this flat chain forever. And that is said to be a poorly mixing Markov chain. But you can make up your own algorithm, what I'm trying to say, based on detailed balance. I think is a really cool and powerful trick. And I am out of time. So that's that. Thank you.